Hi there. Welcome back to the Formulaic Approach channel. Today we want to talk about the structural formula following the video I made on hydrogen bonding. It is expedient that you understand structural formula in organic chemistry. It's going to give you a good start with organic chemistry. Now listen, in this video we are going to be going over the models that exist. It will look like some sort of historical background or like downline of how we modified structures or wrote drill structures in organic chemistry and all of that. Okay? So you will understand why we use particular types of formula and when to use them. Okay? So first, you have to understand, in order to understand structural formula, you must first understand what the empirical formula is. So there are two fundamental formulas, which are the empirical formula, which is the actual fundamental formula, and from which we can derive a molecular formula. So the empirical formula is just the formula that shows you which and which atoms are combined and in which ratios they are combined. So we say it's the simplest formula that a compound can have. So in this case, the simplest formula that an organic compound can have is the empirical formula. For example, you know this is glucose here. C6H12O6. But this is the molecular formula. The simplest form of this formula that shows the ratios of combination of the atoms in this molecule is going to be the empirical formula, which is divide through all this by 2. You're going to get 6 by 6. Divide through by 6. You're going to get 6 CH2O. And this will be the empirical formula of glucose. In fact, much so for most sugars, hexose sugars. Is it clear? All right. So that is what empirical formula is. Now, from empirical formula, we are able to deduce the molecular formula. Now, what's the molecular formula? The molecular formula actually now shows us the atoms that are combined and in the amount in which they are combined. It shows us what the atoms that are combined and the amount of those atoms in the molecule. Does that make sense to you? Let me give you an example in, I want to use a simple molecule. Let's use this guy, for example. Ethanol. Ethanol is going to have the molecular formula C2H5OH, that will be C2H6O. So that's going to be C2H6O. This is going to be the molecular formula of ethanol. Okay? Ethanol is going to have this molecular formula. Now, but you see the limitations of the molecular formula is that it doesn't show us how these atoms are arranged spatially. Okay? So that is why we invented the structural formula, or no, not we, because I wasn't there. Actually, I was there, but you know, I wasn't there. Anyway, so the structural formula is actually the formula that shows us the orientation in space, the spatial arrangement of the atoms around each other in the molecule that we have. Okay? But there are different forms of structural formula. Okay? Now, the one you see in most in your textbooks, the one that we commonly write as scientists, is just to bring this guy here, 2 C's here, and then we have single bonds all through, OH, H, 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 H. Now it shows you this one, this conformation here, or this structure here, makes it to look as though the angle between this guy, this H, this bond and this bond is 90 degrees. And that is wrong, because if you saw the last video, or the first video on Introduction to Organic Chemistry, which I should link in the description below, I already talked about the orientation in space of single bonds because they are sp3 hybridized, okay? So the bond angle is 109.5 degrees, not 90 degrees. But why do we use this? We use it for convenience. Yes, for convenience. So that we'll not begin to rack our head around, where should I put this bond, where should I put that bond? Does that make sense? All right? So we use this for convenience sake. Albeit, the limitations are now the fact that it doesn't tell us the actual orientation in space, the spatial arrangement of these atoms around the carbon atom, and also the existence of isomers. Isomerism does not, the existence of isomerism or isomers also makes it confusing to tell the difference between two molecular formula. Is that okay? Then we also have the fact that free bond, single bonds allow for free rotation about its axis. So because there is free axial rotation, sometimes the molecules can be confusing. Okay, for single bond. So those are the limitations of this. So because of that, the ball and peg model, or some people say ball and stick, is that okay? The ball and stick model was invented where, I remember those days, we will use broom, we'll take broom, and we will eat gum, we'll chew gum, and we will attach. So the ball and stick model for this guy, for example, is going to be something like this. Okay, so where these balls here are representing the atoms, carbon in this case, hydrogen and OH. Okay, so this is going to be the spatial arrangement. So this one, ball and peg model, helps us to identify the spatial arrangement because you can already see that here the bond angle is what? About 109 degrees. Is that okay? 109 degrees. To be as far away as possible as from this bond, as far away as 109 degrees also. Is it clear? All right. So this is going to be the ball and stick or ball and peg model. Okay? But the limitation of this guy also, this guy makes it look like, if you look at this now, you may be wondering that all of these balls I drew here are carbons, all carbons. By the way, I was talking about how we did it in those days. Just take brooms, then chew gum, put gum here, use a toothpick, attach to this gum, and put a gum here, attach to this gum, put a gum here, and then attach to this gum again, put a gum here, attach, and like that. So those, it will now represent the molecule. We use methane that time though. So it's going to look something like this. Put a gum, put toothpick, a gum here, toothpick, a gum, toothpick, a gum, toothpick, a gum, and toothpick, a gum. Okay? So you're going to have this. This is your ball and stick model using chewing gum. So you see, the point is that this ball and stick model actually helps us to understand the spatial arrangement of those atoms around the carbon, but it doesn't, it almost presupposes that the atoms are alike. While in fact, we know that there may be different atoms here because in this case we have OH group. And oxygen has a greater atomic radius than carbon and than hydrogen. So if you look at it now, you think everybody is hydrogen here. No. Okay? So this is where the Stuart model. So the Stuart model now came to help us to be able to tell the size of to be able to tell the size of the molecules that are attached. Okay? So the size of each ball you now see will be proportional to the atomic radius. Of course, you know the atomic radius is very small, but like once you see a bigger ball, you know that it has a bigger atomic radius or is a bigger atom than the former atoms you've been seeing before. Does that make sense? All right. So we have the Stuart model as the second model. So the Stuart model, now the problem with Stuart model is that it pretty much doesn't really show us the bond length. So this shows us spatial arrangement and maybe even bond length. Because by the time we'll be drawing both some double and single bond, you will soon see that the double bond, the single bond, the sp3 bond is less, sigma bond is longer than the sp2 bond. I've already talked about that, yeah? So this one shows us that, but the Stuart model doesn't. It just uses balls. You know, imagine I drew something like this and I used ball of equal sizes and I put this here, put this here, put this here, put another hydrogen here, one hydrogen here, then I put a bigger ball here. So this to show you that carbon has a greater atomic radius than these guys. You see that their sizes are almost the same, right? These two guys are the same, so this carbon. Then this one that is away here is oxygen. It's going to have a greater atomic radius. All right, so what does this tell you? This shows you their atomic radii that are different, but you see it's harder to read in terms of spatial arrangement than the ball and peg model. Then the third model is the Dryden model. The Dryden model. Now the Dryden model is of two types. It uses what we call the boat conformation and the chair conformation. Yeah, you're going to draw a boat or you're going to draw a chair. All right. The thing is that we use this Dryden model for molecules that are large and we want to use to examine their stereochemistry. Is it clear? For example, when we get to sugars, aldehydes, exo sugars, we are going to see how something can transform. You can transform it from the chair conformation to the straight chain, or the straight chain Haworth projection to the chair conformation. Does that make sense? All right. And the Newman's projection and the Haworth convention. Yeah. You are going to see it, don't worry. So it looks something like this for the boat conformation. You're going to see something that looks like this. Something like this. You know, you may not be, I'm not perfect at drawing it, that's just the point. So this guy is going to show here, is used for this cyclohexanes, okay? Cyclohexanes, or even bicyclos. I have this. So each point here, or vertex here, represents carbon atoms. Is that clear? So I have an atom here, another atom here. You see, this shows you, and you see it's usually perfect. The Dryden model, these conformations are usually perfect representation in spatial arrangement and bond length and all of that. Is it clear? But it's used to study the stereochemistry, don't forget that, of large molecules. So I'm going to have something that looks like this, this. Is it clear? So this is the boat conformation. This is not linking to this. This is not linking to this. Is that okay? So single bonds, cyclohexane, hexane 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Hexane. Then the chair conformation of this guy is going to look something like this. You have this. Just follow me as I'm drawing. Just draw a triangle that looks like this. Then a little bit slimmer. Then bring this guy down here and bring this guy down here. So when you do that, no, not like this. Just bring it straight and make it straight, okay? Maybe not so straight, but don't bend it too much. Then this one will go like this if you want. Or you could start like this, okay? And you bring this guy here, bring this guy here, bring this guy here, and you take this one down. You see that? It looks like chair, yeah? Okay, so then you now begin to draw your molecules. For this one, it's going to look something like this, this. These are the atoms on it, that I'm drawing there. So this, and this, and this, 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 and this. All right. So that is the Drayton model and the chair and bolt conformations. All right. Then the other formulas that you should now know that we normally use is what we call the condensed formula, condensed structural formula, and the skeletal formula. Skeletal formula. Now the condensed formula is simple. It will only show the molecules, but it will separate them. Is it clear? Is it to separate them according to the ones that are attached to which directly? Okay? So for example, this carbon is directly attached to this and this and this, right? So we have, for condensed formula, the condensed formula of ethanol, before I draw the skeleton, the condensed formula of ethanol is going to be what? CH3, okay? You can put your H3 in front too, only that I like to draw it in such a way that my bond will proceed from C, okay? So I draw this. So sometimes the condensed formula might show the bond, other times it might not show the bond. So C here, we have H2, does that make sense? Then we have OH, OH. Is this clear? All right, so this is going to be the condensed formula. Then, of course, you can put a bond there if you wanted, but this is the condensed formula. It's, you know, if I have something like this now, and I wanted to write the condensed formula, it's going to be like this. CH3, 1, 2, 3. Then, now, I could decide, because this is CH2, 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 CH2. No, CH2, 3 CH2s rather, before the CH3. Now I could say CH2 occurring 1, 2, 3, 3 times, then CH3. Does this make sense to you? Okay, God bless you. And you can decide to put your bonds if you wanted. But I'm not putting bond in this. I put bond in this. Is it clear? That's condensed formula. Then the skeletal formula is just for speed and, you know. So if I wanted to draw this, the skeleton of this, I'll just use these strokes only. We use strokes only for skeletal formula. Skeletal formula. So if I want to draw this is 1, 2, 3, 4, 5. That's pentane. That's going to be 1. Sorry, here's the way you count. You count from the point you drop, you put your pen on the paper. So we have 1, 2. Does that make sense now? So 1, 2, 3, 4, 5. So each vertex here is going to represent what? Carbon atom. So away from which you now have your hydrogen, 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 hydrogen. Does that make sense? All right. Then if I wanted to draw double bond, this is how we draw double bond. So now listen here, because of this skeletal formula, some people make mistakes with it. So if I wanted to draw maybe pentene, I'm going to draw something like this. 1, 2, 3, 4, 5. Then put my double bond here because it's pentene. Pentoene, like this. Does that make sense? You will also notice that it's showing that the single bond, the sp3 bond, is longer than this, the second bond, pi bond here, the sigma and the pi. Does that make sense now? You're loving it, yeah? Okay. But if you want to draw the triple bond, it's different. Let's say I wanted to draw pentyne. It's going to look like this. Watch. Now you know that pentyne is this. 1, 2, 3, 4. 1, 2, 3, 4. Then 1, 2, 3, 4, 5. This is pentyne, okay? Now the way I'm going to draw it is, I'll draw 1, my first carbon. Do you see this? 2 pi bonds. Then listen, I will continue with a straight bond. Is it clear? Then before I now curve and curve and curve. Do you know what this means? This shows you that there is a linear molecule here. So let's count the number of carbons that we have here. The number of carbons we have here. We have 1, 2, 3, 4, 5. Does that make sense to you? This is going to be a linear molecule here. Let me show you. What if this triple bond was in the middle? This is where you should listen, please. So we have 1, 2, 3, 1. Then what if it were here? Now let's put it here. One, two, three, 4. I just want to draw it. 1, 2, 3, 4, 5. I just want to draw with paint. Okay, so how would you name this? By the way, I've covered naming videos, so I will link it in the description. Now how do I draw this in skeleton? I will show my first carbon, 1, second carbon, 2. Okay, you see I went up, right? Or you can go anywhere. Let me draw it here. This will become my first carbon, 1, second carbon. Let's say I go down here, second carbon. Between second and third carbon, I have a linear molecule, triple bond. Okay? Then, between this, so I have, this is my third carbon. Okay, in fact, this is where you're supposed to draw it. 1, 2, 3. So that is going to be first carbon, second carbon, third carbon, fourth carbon, fifth carbon. Do you understand that? First carbon, second, third, and fourth, and fifth carbon. So it's at the fifth carbon we kinked to show you that there is a linear molecule in between, because you know the bond angle for triple bond is what? Linear. All right, that will be all for this video. We are going to go into spectrometry of organic compounds in the next video. Before we begin to see mechanisms of reactions, effects of polarization, inductive, mesomerical, center. All right, do not subscribe to the channel, please, and God will bless you. And share the video.